Welcome. Let's discuss the idea of limits in rational functions. So let's say that we're interested on finding the limit at some location. Let's call it C of some rational function where nx is the numerator and dx is the denominator. Well, there are three cases that we need to consider. Let's look at one case at a time. In case one, let's say that when we evaluate the rational function at some number, let's call it C, and I represent that as n, which is the numerator, evaluated at C, divided by d, which is the denominator, evaluated at C as well. And this evaluation actually gives us some number, whatever that is. Then we can actually say that the limit exists and it is equal to whatever number we obtain. So let's say that here we have our rational function, and what we are saying is that at some number, let's call it C, the function is continuous, and the limit, it is the evaluation. Let's give an example of that. So let's consider the rational function of x squared plus x minus 6 divided by x plus 3, and let's find the limit at the location of x equals -1. Let's start by evaluating the function. So our first term, 1 to the second, that's +1, then -1, then -6. And on the denominator, we got -1 plus 3. Now, 1 and -1 is going to cancel out. So on the numerator, we just get -6. And when we combine the denominator, that's equals to +2. And now we obtain the result of -3. So we are done. The limit of the rational function x squared plus x minus 6 divided by x plus 3 as x goes to -1, that's equivalent to just -3. And it's a simple evaluation because the function is continuous at the value of x equals -1. Let's grab the function and let's verify this. So how about we take a look at the table of values of the rational function? And now we can see that when x is equals to -1, we have a coordinate point where y equals -3, which shows that it was continuous at this location. So let's look at a second case that maybe we can encounter. Maybe when we look at the numerator and the denominator and we evaluate it at some number, let's call it C, we obtain the result of 0 divided by 0. Well, when this situation happens, the limit still exists. Because what we have a hole in the graph. So let's visualize that. So let's say that here we have our function, then at some value of C, we have a hole in the graph. The limit still exists because we are still reaching the same destination from the left as we do from the right. And what we are going to do when we encounter this scenario, we are going to simplify and then re-evaluate the function. Let's show an example of this. So how about we get the same rational as the previous example, but now we are interested on the limit as it goes to -3. Let's start by evaluating the function. At the location of x equals -3. But let's simplify this. -3 to the second, that's 9. -3 minus 6. And on the denominator, we got -3 plus 3. On the numerator, we got 0. On the denominator, we got 0. So what this is saying is that we have a hole in the graph at the location of x equals -3. So how about we simplify? And let's evaluate one more time. Well, the numerator, x squared plus x minus 6, we can factor that out. We can factor it as x minus 2 times x plus 3. And on the denominator, let's keep it as is. Well, now notice that x plus 3 is going to get canceled out. And now we just have the expression of x minus 2. Now let's evaluate the simplified expression. at the location of -3. And now we have a result of -5. So what we are saying is that the limit of the rational function x squared plus x minus 6 divided by x plus 3, as x is approaching -3, it is nothing more than the value of -5. Let's visualize this result. So on the right, we have the graph of the rational function that we were given. And notice that at the value of x equals -3, the function is undefined. But at the location where x is equivalent to -3, we should have a hole at this location. And as I'm approaching this value from the left, it is the same location as I do from the right. And the value that we are approaching is y equals -5. So the limit still exists. So the last case, it deals with the same scenario. Let's say that we have a rational function and we want to find the limit as we approach the value of c. Well, how about we want to do this in an algebraic way? So let's evaluate the top and bottom by that location, which is c. And now let's say that we end up with some number on the numerator, whatever that is, it's just some number, but only the denominator is equals to 0. Well, in this case, the limit does not exist. And the reason behind it is because we have a vertical asymptote. So let's illustrate this idea. Let's concentrate on some x value, let's call it c. And now let's draw some vertical asymptote. Well, because my function cannot be evaluated at this vertical asymptote, then maybe I have my function going up and down at this specific location. They do not agree on the same orientation. As I go to the left, I'm going up. And as I'm coming to the right, I am going down. Well, maybe you're saying, well, what if on the left-hand side, I'm approaching up, and on the right-hand side, I'm approaching up as well? Well, it is true that you are going on the same direction from the left and the right. But what is that direction? Do we know the value that we are approaching? The answer is no. So technically speaking, by the definition, we can say that the limit does not exist. So let's give an example of this. So let's consider the rational function of x squared plus x plus 6 divided by x plus 3. And let's say we want to find the limit as x is approaching -3. Well, let's start by evaluating the function at the location of -3. In the numerator, we're going to get 9 minus 3 plus 6. And on the denominator, we're going to get -3 plus 3. The numerator, we're going to get 12. And the denominator, we're going to get 0. So at this point, we can stop because this shows that we are going to get a vertical asymptote at the location of x equals -3. And we can conclude that the limit as x is approaching -3 for the rational function that we were given does not exist. So let's graph this function and let's verify this result. So the graph on the right represents the function that we were given. And notice that we do have a vertical asymptote at -3. And notice that the directions, they do not agree. From the left, as we are approaching the value of -3, we are going down. And from the right, as we approach in this location, we are going up. The limit does not exist. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.